I want to design a fully automated factory that can build each of these 3 Lego cars. Let's start off with just this car and see if a factory can build this. My first thought was to build a simple claw mechanism that can reach down to pick up each of the parts of the car and then move them around. I realized pretty quickly though that this would be nowhere near precise enough to place the parts down exactly on top of each other, and even if it could, it wouldn't be able to apply enough force to properly push the pieces together. Instead, I made this 3-axis positioning system which can move this attachment to anywhere within the machine, from side to side, front to back, and up and down to the platform below with the high force output of these linear actuators. At the bottom it's got a lime green piece like this, which will be what picks up and puts down the pieces. It's a bit of a funny looking piece, but it's got an anti-stud here in the middle which lets it attach to the studs on top of any Lego piece. So unlike the claw I showed earlier, this machine can line itself up directly over the piece it wants to pick up and extend the green piece down to grab it. The linear actuators above apply enough force to press the grabber down fully onto the orange brick, and then it can lift it right back up off the platform. The machine can then carry this brick all the way over to this other platform. You might be wondering how this machine will be able to place the pieces back down, but that actually turned out to be very simple. The machine can firmly press the orange brick down onto the platform, and then when it retracts back up, the green piece simply pops out and leaves the brick in place. The reason all of this works is due to the number of points of connection between the different pieces. When the machine first goes to grab the orange brick, the brick is just resting freely on a towel underneath, so there's nothing holding it down, and when the grabber reaches down to take hold of it, it can lift it up with ease. But when the machine goes to place the brick back down, it pushes it down onto all 4 of these studs. Comparatively, the grabber is only connected to the brick with a single stud here. This means that when the grabber starts retracting back up, there's a lot more force holding the brick to the platform than there is holding it to the grabber, so the grabber separates off instead. And if the machine then goes back to grab another piece and brings it over to attach it on top of the first one, then the same principle will apply here, and the brick would stay in place while the grabber moves away. And bear in mind that this time there were only 2 studs of connection holding the brick down, but that's still more than the 1 stud that the grabber piece was connected to. So as long as the pieces are all placed down onto more than 1 stud, this principle will work and the factory will be able to assemble the car piece by piece. Now, it really cannot be overstated the level of precision that this machine needed in order to perfectly align itself directly on top of each of the pieces, so that when it extends down to grab them, the green piece slides down exactly onto the stud to make a proper connection. If the grabber is misaligned by even a fraction of a millimeter in either axis, you can see that it gets completely stuck in that position and won't take hold of the piece. And because of that, everywhere you look on this machine, every single thing was designed with precision in mind, because for the grabber to move in all 3 axes and stop in the exact perfect position, the precision of everything had to be right on the limit of what was possible with Lego. Starting off with the rails that the machine runs on, I first tried just using some lift arms to constrain the structure to only slide back and forth, but come on, this is nowhere near precise enough for what we need. So I instead looked at these long axles. Since they're designed to fit and rotate smoothly within Technic holds, they've got a pretty tight tolerance, and there's not much play at all. So I used 2 of these axles as rails on either side to constrain the motion of the structure to just forwards and backwards. While these are rigid enough to maintain the position of the structure, they wouldn't be strong enough to support its full weight, so I added these rollers to bear its weight as it slides back and forth. The next challenge was figuring out a way to control the movement of the structure. A simple solution would have been to attach gear racks to either side like this, and then to use a gear to move the structure back and forth. But even if we connected the motor we'll be using directly to this gear, there would already be too much backlash just between the gear and the rack. It might not seem like much, but this tiny bit of play between the pieces really would be the difference maker between the grabber sliding directly onto the stud and picking it up, or it being misaligned and getting completely stuck. I instead decided to use a long chain link like this that wraps around the whole structure and attaches to it here at just this one point. Right now it's really slack though, which again introduces backlash into the system. To prevent that, I added this tensioning mechanism to the other end of the chain. With the use of a linear actuator, it lets me select the exact amount of tension that I want in the chain, and once I've set it like that, it will stay rigidly in place. With the chain properly taut, there's pretty much no backlash when I turn the gear, and I can adjust the position of the structure with a really high level of precision. Of course, if I only use a chain like this on one side, it will just twist the structure instead of pulling it, so I added the same chain and tensioning mechanism to the other side. In terms of the motors I'll be using to power this, I'll be relying on these Mindstorms motors and hubs, so that I can program the exact amount I need the motors to rotate. One of these hubs only has 3 slots for motors, which means we'll need one motor for the front to back motion, one for the motion side to side, and one for the motion up and down. So in order to drive the chains on both sides with just a single motor, I had to run a long axle along the whole length of the machine to connect the gears on either side. But once again, take a guess what problem I ran into. Too much backlash along the axle. It may seem like this axle twisting a bit wouldn't make much of a difference, but you can clearly see that the left side of the structure moves by less than the right side. And with the level of precision we need here, that small discrepancy would be enough to throw everything off. My solution was to thicken up the axle, so that, over the same length, it twists by a lot less. Granted, there's still a bit of backlash, but you can see that the movement is much smoother than before, and I was hoping that any backlash left would be well within the margin of error. With the front to back motion connected to the motor, I then had to do the same thing for the side to side motion. I built a similar frame with rails and rollers within the structure to let the grabber assembly slide sideways, but fitting in the chains to move it proved to be quite a challenge. I couldn't really put them out here on the sides because that would reduce the travel distance of the structure front to back, so I had to fit the chains through small gaps in the superstructure all the way to the outside ends here to drive them to pull the assembly. It looks a little tricky, and to be fair, it is a bit of a tight squeeze between all the different mechanisms, but it does work quite nicely. I was a bit worried that these sets of chains overlapping like this would get stuck on each other, but luckily that didn't end up being a problem at all, and all the chains moving in both axes can slide past each other with no issues. On this side of the structure, it was simple to add on a motor between the gears to power them, which in turn moves the central assembly from side to side. And since these motors have pretty long cables, it works out fine having the motor move from side to side with the rest of the structure. And again, I needed to add a tensioning mechanism for the chains. I could have again used linear actuators for this, but that would have made the structure stick out pretty far here, and I was sure I could find a way to make something more compact. Well, this is what I came up with. At first glance, it might not seem all that compact, but that's because it had to be more complicated than I originally thought. As it turned out, the 2 chains will always need to be tensioned individually, because despite them both using the exact same number of link pieces, the 2 chains will always be slack by slightly different amounts. I think this is likely due to very small variations in the flexibility of the chain link pieces, which add up across all the links. And if you think about it, it kind of makes sense. Even with very tight tolerances on the length and stiffness of the chain links, even if the links on one track stretch apart by just a tiny, unnoticeable amount more than they do on the other track, when you string together all 100 or 200 of those links, that adds up to a still tiny but now noticeable difference in length, which you can see here by the fact that I had to tension them by different amounts. I've also found that the chains often get looser over time, so depending what links are older and newer, that could also explain some of the difference in length. I could also spend a while gushing about all the tiny details of this design, like how these worm gear pieces are actually just free to slide out here, but I can be sure that they won't because the tension in the chain will always be pulling on the gear in this direction, which gets transferred through these linkages and will be always acting to push the worm gear downwards and never upwards, so it will always stay fixed in place and maintain the right tension in the chain. Well, I guess that's the main cool thing about it, apart from just some clever part usage. And with that, the machine could now move in 2 of the 3 axes, which just left the grabber mechanism to make. The only challenge here was to make it compact enough to fit within the sliding structure. But with that done, and the assembly in place within the structure, I simply hooked it up to the final motor. This motor is also attached to the superstructure, so it can move back and forth lengthwise with it. And I used one of these frictionless gears that can slide freely up and down axles to power the grabber assembly even as it slides from side to side along the structure. And altogether, this allows the grabber to move to any point in this area, and extend and retract there in order to grab a piece. I also tried to make the grabber assembly as rigid as possible by using all of these guide rails, as if the grabber could bend from side to side, that would again reduce its precision. So now that I've explained how this whole machine works, it's time to finally explain how I want to use it to actually build the car. While the grabber mechanism is very capable of assembling pieces, it is just limited to pushing them down vertically on top of each other, and the pieces need multiple studs of connection, as I explained earlier. So I knew it wouldn't be possible for it to assemble a car as complex as this piece by piece, given how many advanced building techniques it uses and how many pieces are attached on sideways or even upside down. So instead, I made this abridged version of the car, which can be separated out into these 7 sections. We've got the chassis of the car, the front wheels, the rear wheels, the engine, the front half of the body, the rear half of the body, and finally the windscreen, to form the full car. Since all of these sections are attached directly on top of each other, the factory should hopefully have no trouble assembling them. First off, I built this pallet, which holds all 7 of the car's sections in place, and I fixed it down onto this side of the factory. There's a little bit more to my plan though, because if the grabber did just pick up each of the car's parts one by one, carry them over to this platform, and then press them down over here, then sure, if everything works as intended and the factory can attach on all the pieces, then by the end we would have a completed car, but it would just be stuck down rigidly onto the platform. As I explained before, the grabber would just break off, rather than lifting the car off the platform, so it would just be stuck here. So instead of using a basic platform like this, I built this specialized one, which has these 2 prongs that stick out on top of the bed where the car will be assembled. And I built this whole mechanism around the side, which is connected to these 2 buttons. Pushing on the green button retracts the prongs back, and pushing on the red one brings them back out again. So my plan here is that when the grabber carries over the first section, which is the bottom of the chassis, instead of pushing it down, it slides it in under the prongs. It can then lift upwards to detach itself and leave the chassis in place. The grabber would then attach on the front and rear wheels on either side of that, and since the prongs are holding the car down, it will stay in place each time the grabber lifts away. The machine would then attach the engine on top of that, which also covers the prongs. It would then attach on the front of the body, and then the rear of the body, and then the windscreen. And still, the car is held down and the grabber can disconnect and move away. But now that the car is complete, the grabber can move over to here and push down on the green button. That pulls the 2 prongs out from the car, so now it's free to move. And then if I just add a ramp to this side of the platform, the machine should be able to simply push the car down and right on out of the factory. That's the plan at least. So now it's time to program the machine and see if it can actually perform all of those operations. Oh yeah, another thing I wanted to mention about the mechanism with the buttons is you can see here that the prongs have these thicker sections on their lower side, which stick out right to the edge of the platform. The purpose of those is to align the chassis to the correct position when the grabber slides it onto the platform, because, as I've painstakingly mentioned, the precision is extremely important here. But if those prongs were able to just slide back and forth freely, then when the chassis comes in, there's a good chance it might knock back the prongs a bit, which would mess up the whole alignment. My solution was to make it so the prongs get locked in place when they get pushed forwards. That's all thanks to this lever mechanism down here. When I push the button all the way down, the lever locks into this lower position, so that no amount of force pushing on the prongs is going to make it move back out. And yet, when I want to release it, it still takes a relatively small force pushing on the green button to unlock it and retract the prongs back out. And if you ask me, it makes for quite a satisfying mechanism. This is how it looks when I've slotted it in inside the factory, and here is the ramp which will lead the car out when it's done. A few days of programming later, and I was ready to give the whole machine its first test. So starting off, the machine moves over to the first part and extends down to grab it. Well, that wasn't a promising start. It already missed the studs and retracted back empty-handed. Okay, how about giving it a second try? Let's see if it performs any better. And okay, great. That time it actually picked it up. So now, once it's retracted back up, it should carry it over to the other platform and try to slide it under the prongs. Okay, we've just got to wait for it to extend down, slowly. Yeah, it failed once again. But I do think that is a problem I should be able to solve fairly easily. But okay, if we assume that it did slide in properly, let's at least see if the grabber can pick up the next part, which is the rear set of wheels. It was already seeming pretty clear at this point that I had some major accuracy issues still to deal with, and this time it again failed to pick up the parts. But after giving it another 1 or 2 attempts, I managed to get one where it did correctly pick it up. So let's see if it can attach this one down. I'll speed it up and cut to the chase here, but again, no success. It simply wasn't aligned well enough, which makes, 4 for 4 on things it did wrong? And I was facing all of these same issues when filming each of those clips from earlier in the video, and it always took a load of attempts before I got one where everything lined up properly. And I'll be honest, when I first did this test and got these results, it was a fair bit demoralizing, but I can confirm that by the end of this video, each and every one of these issues will have been solved. But after spending a few hours questioning if a car factory like this was even possible, I came back to it with a clear head and a whole list of possible improvements to make. The first and easiest one was to make these side edges of the car chassis curved so that they wouldn't get stuck on the prongs. And to my surprise, on the very first test I did for this, it worked like a charm, and the piece slid in perfectly. Next, I wanted to see how I could make the whole factory more precise. The motors I've been using to power it are accurate to the nearest degree, and with these sized gears driving the chains, that works out to an uncertainty in the grabber's position of plus or minus 0.11mm, which is tiny, like really tiny, to the point that I would have thought this would be more than precise enough. But I thought, hey, there's no harm in trying to make it even more precise. One solution would be to increase the gear ratio, so that the chain moves by a smaller distance for a given amount of rotation of the motor, but the backlash between the gears would be enough to make the whole process redundant. The other option was to make these gears themselves smaller. I couldn't make them too much smaller, and this is my reasoning if you're interested, but going down from these 24 tooth gears to 16 tooth gears seemed to work fine, and doing this reduced the uncertainty in the position of the grabber by 33%. Giving it a test though, you might be surprised that it still didn't really help the problem. I've got a few thoughts on why this might be. Firstly, while I did try to make the whole structure as rigid as possible, just by the nature of its size, it can wobble back and forth a bit, which might be enough to throw off the precision. Secondly, the precision of the machine is only as precise as its starting point. So even if the machine itself is accurate to 0.1mm, I am certainly not that accurate when I'm trying to align it in the right position before I start using it. You'd think this would be as simple as just lining the structure up with this back edge, but since all Lego pieces inherently have some small gaps between them, if the pieces are actually touching, it means they're too close. So is this the correct alignment? Or this? You can see how getting the exact right positioning here is kind of challenging. That's definitely not the only factor here though, because if it was, the grabber would be offset in the same direction from all of the studs, but in reality, I found it to be quite hit or miss with when it was and wasn't aligned. To prevent all these misalignments, I had to think about how you and I actually put Lego pieces together. We don't just push them vertically downwards and expect them to line up perfectly, or at least I don't. We normally tend to apply just a bit of pressure between the pieces and then slide them around until they slip into the right spot, and then push them in from there. So I wanted to apply the same principle to the machine. To explain how I implemented this, let me briefly show you how I went about programming the movements of the grabber assembly. Working out the exact position in 3D space that the grabber needs to move to in order to pick up a piece, and then the exact path it needs to take to move between the platforms was surprisingly difficult to keep track of. So first off, I assigned a coordinate system to the machine, with X, Y, and Z being defined like this. I then built this 3D grid to give myself a proper representation of every point the grabber needs to move to during the entire assembly process. This large grey square represents the pallet, which holds all of the car's parts. This smaller square represents the assembly platform, and all of these coloured squares represent each of the points in 3D space that the grabber has to move to during the assembly process. They're all colour coded, with each colour representing the sequence of moves needed to attach one of the 7 pieces to the car, and this is the colour code if you're interested. Red represents the first part, so this tells us that the grabber has to move over from its starting position here over to this spot. It then has to retract down to this position to pick up the piece, which is marked with a round plate. It then moves back up to here, across to here, here, down to there, and slides in onto the platform, before moving up to retract itself from the part. The next colour is green, so it moves over to here, and does this whole sequence like this to attach on this part. Then it goes to blue, and does all of that, then purple, then lime green, then yellow, then pink, then dark red, and finally back to the start position. And once I'd laid all of this out, it was just a case of counting up the distances in each axis between each of the consecutive parts. I recorded all of these in this spreadsheet, which let me easily convert the studs of travel in each axis to degrees of rotation for each of the 3 motors, which I could then use to program the machine with the correct movement sequence. And with this many steps needed to fully assemble the car, putting it in a spreadsheet like this really was the only feasible way to go about it. And you've got to bear in mind that, like with most real robots, I had to be very careful with the coordinates I told it to move to. because if I accidentally gave it coordinates that are outside the edges of the machine, well, that happens, which is never what you want to see. And by using this spreadsheet, I was able to add in all of these extra movement steps between the main operations, which will help to properly align the pieces each time the grabber has to pick them up or push them down. So now, instead of pressing all the way down, the grabber extends down just far enough to apply a small bit of pressure between the pieces. It then does this quick wiggling motion, which all but guarantees that the grabber will find the correct spot and snap onto the stud. It then presses down fully and can then retract back up to lift the piece off the pallet. And this wasn't just a one-off success. As you'll soon see, each and every time the grabber has to pick up or push down one of the pieces, it does one of these quick wiggles to properly align itself, and it works pretty much 100% of the time. What you're seeing here with these quick wiggles is the grabber tracing out a small square like this around the stud before moving back to the middle, and it really amazed me just how well this works. So with that said, I think we're ready to do a full assembly test. The grabber starts by positioning itself directly above the bottom chassis section, and then extends down to grab it. It then does that quick wiggle to align itself before pressing all the way down, and then lifts the part back up. It then carries it over to the assembly platform, slides it in under the prongs, and then retracts up, leaving the part in place. It then moves back over to the pallet and reaches down again. It does another wiggle and then lifts up the second part, which is the rear pair of wheels. It carries them over to the platform and then begins pushing them down in the right spots. What you saw there was a bit different to the other wiggles because it was able to align the part by pushing it just inwards right against the other part and then just doing a wiggle from side to side, and that motion really ensures that it's in the correct position. You will see that again here with the front wheels. Yeah, if you look at that, it slides the part inwards and then just does a wiggle side to side to make sure it's properly aligned. Next, the grabber goes over to the pallet to pick up the engine block. It retracts down, does its wiggle, and picks it back up, and then it carries it over. Once again, it presses it down and does a wiggle to make sure it's in the right spot before pushing it all the way down. Next, it picks up the front half of the body of the car. Again, it does the wiggles as it lowers the part down, but if you saw there, it actually does two separate wiggles at different heights, based on when the pieces are at risk of getting stuck. And you'll see that again here in a moment with the rear half of the car body. Because of how large this section is, the grabber couldn't lift it high enough to carry it over the other parts, which is why it had to take that long path between them to get over here. And again, if you saw, it had to do multiple different alignment operations at different heights to make sure the body slots into the correct position. After that, the windscreen is the final section, so once the grabber is done attaching it, with a wiggle of course, it moves over to the green button and starts extending down to push it. Doing that releases the two prongs that were holding the car in place, and then the grabber simply pushes the car right along and right out of the factory. I've watched the machine do all of this many times at this point, but every time the car rolling out of the factory is just so satisfying. I also wanted to show the full uncut assembly process in at least one clip here, just to show that there's no editing trickery going on and that the factory can reliably build the whole car with no mistakes. And that's why I've been so focused throughout the whole video on ensuring that the precision of the machine is as high as it can possibly be, and why I've spent so much time showing the lengths I've gone to improve its consistency when it connects to the pieces. Just take the alignment wiggles for example. Before I added those, the chances of the grabber successfully picking up each piece were probably around 20%, and even lower for when it had to push the pieces down on top of each other. But now with those wiggles, I'd say it's somewhere around 97 or 98%. And if you think about it, just to build the one car, the arm has to pick up the segments 7 times and attach them onto the parts below 6 times. So that's 13 instances where the studs of the pieces have to fit exactly together. And if they're misaligned, even by a fraction of a millimeter, the grabber will get stuck and the whole assembly process will fail. So even with a success rate of, let's say 90% each time the parts have to connect, when that's repeated 13 times, it starts to become incredibly likely that there will be at least one failure. And now it's just finished, but let's see if it can build the car twice in a row. In the same take, I'm now going to take apart the car, put all the pieces back on the pallet, and run the whole assembly process a second time. Of course, I'll speed it up more this time, but hopefully this illustrates my point that the factory is indeed very reliable. It's nearing the end already, and that's looking pretty good. And here it is, the finished car once again. And here is an overhead shot of the whole assembly process. I haven't ended up showing many shots from higher up angles like this, just because the grabber frame is in the way a lot of the time, so it's harder to see what's happening. But it is still fun just watching the car coming together piece by piece. And also, at the start of the video, I said that I wanted to design a factory that could build all 3 of these LEGO cars. But right now, with how it's currently set up, it can only build this one car. My plan for that is, I want to make it so once the factory finishes building this first car, the whole pallet will slide out of the way, and a new pallet with all the parts needed to build the second car will slide in to take its place. And then, when the second car's done, the same thing can happen and the pallet for the third car can come in. But believe me, that is not going to be a small job, and this video is already quite long, so I'm going to tackle all of that in the next video. And also, I've got some more ideas to try and improve the reliability of the machine even further. So thanks for watching, and before I go, hope you enjoy one more time-lapse of the factory doing its thing. You know, looking back, I'm really happy I made that spreadsheet to plan out all the movements of the machine. Because you know, over the course of assembling the car, it goes through over 100 operations, not even counting all the wiggles and alignment steps. And even this way, it took a while to program. But I've got to say, it sure does make for a satisfying end result. And that's about it. So thanks for watching, and see you in the next video.